We're going to discuss eigenvalues and eigenvectors. Let's suppose we have an n by n matrix A, and n by n means that it's a square matrix. And let's also assume that this matrix could have complex entries. So we can include things like 4 plus I as an entry in our matrix. And suppose we have a column vector x that can also take complex entries. But assume that this matrix, this column vector here, x, is not equal to 0. And I also want to assume that A times x is equal to lambda times x, where lambda is a scalar. So it's just some number, some complex number. So what this is saying is, if we take this square matrix and multiply it by this column vector, we're going to get a column vector. But this is actually a special column vector. It's the actual column vector we originally multiplied A with times some number. So we call this vector x that has this property an eigenvector. And we call the scalar that's in front of the x an eigenvalue. We're going to look at an example of this so to make sure we really understand what's happening. So let's let A be this matrix 2, 7, 4, 5. This is a 2 by 2 matrix. And let's let x be a vector x1, x2. Well, first off, this is any vector x in C2. If we take A and multiply it with x, we get 2, 7, 4, 5, x1, x2, which is 2x1 plus 7x2, 4x1 plus 5x2. So we can think of A as a linear transformation from C2 to C2. Okay. What happens if I choose a specific vector, let's say the vector 1, 1? What is A times x? Well, this is, you can use this formula here, 9, 9. But what does this vector have in common with this one? Notice that's just 9 times this vector. So A times x is 9 times x. So we found an eigenvector, 1, 1, and an eigenvalue, lambda, which here lambda is equal to 9. Now this doesn't work for every single vector. You can see that if I plug in something different, we can even go with something like 1, 0. What do I get? I get 2, 4. And 2, 4, let me erase this so we don't get confused. 2, 4 is not a linear combination of 1, 0. It doesn't matter what you multiply 1, 0 by, you're never going to get a number down here. So you can see that 1, 0 is not an eigenvector. It doesn't have an eigenvalue attached to it. So a good question is, what are all the eigenvalues and eigenvectors that are associated with a matrix? Are we limited on the number of eigenvalues? Are we limited on the number of eigenvectors? How do we find them? Because it looks like it could be a difficult problem. You can see that with this basis vector, for one of the basis vectors for R2, it didn't work. So how can we find these eigenvalues and eigenvectors? Okay, well, let's say that a matrix does have an eigenvalue. Let's call it lambda. Well, if it has an eigenvalue, then that means there's some column vector x such that a times x is equal to lambda times x, and we're assuming that x is not equal to 0. That was the assumption at the very beginning. So we only call things eigenvalues and eigenvectors when x is not equal to 0. Well, if this is true, I can move everything to one side. And that's because this right here, this is a n by 1 matrix, this column vector, because this is n by n times an n by 1. So this product is going to be n by 1. And this is just a number times an n by 1 vector, so this is n by 1. So I can move everything to one side and subtract them. That's fine. And also, if I have a matrix X, which is n by 1, I can always multiply it by the identity, the n by n identity matrix, and I'll still get the vector X. So what I'm going to do is I'm actually going to insert this I right here, because it's not going to hurt anything if I do that. A times x minus lambda times I times x is equal to 0, because this is still x. Okay? I'm going to take this one step further. I am actually going to pull this x, pull it out to the back. So this is a minus lambda times I in parentheses times x is equal to 0. Now we have two matrices being multiplied together. This one is an n by n matrix, and this one is an n by 1 matrix, and we're ending up with an n by 1 matrix. So two matrices being multiplied together, and we get a 0 matrix. Well, it doesn't work for all sizes of matrices, but it happens to work in this case. If this happens, and since this column vector is not equal to 0, A minus lambda I is actually the 0 matrix, the 0 n by n matrix. So since A minus lambda I is equal to 0, and they're both square matrices, we can take the determinants. Because the matrices are equal, their determinants are equal. So the determinant of A minus lambda I is equal to the determinant of 0, while the determinant of a 0 matrix is 0. So we have an eigenvalue, lambda, if the determinant of A minus lambda I is equal to 0. This expression here, this determinant, is actually a polynomial in terms of lambda. And this polynomial is called the characteristic polynomial. So the characteristic polynomial is P of lambda, which is going to be equal to the determinant of A minus lambda I and it's a nth degree polynomial. So if A is an n by n matrix, then this polynomial is going to look something like this. So the power here is n for this polynomial, and these are just complex numbers. And the eigenvalues are the roots of this polynomial. Let's put an exclamation mark there. So if we want to find all the eigenvalues, we just needed to take the determinant of the matrix A minus lambda, where lambda is a variable in this case, and lambda times I, take the determinant of this matrix, set it equal to 0, and factor this polynomial, and we'll be able to find all the eigenvalues. So here's an interesting fact. An nth degree polynomial factors over C. So an nth degree polynomial factors, let's put in linear factors over the complex numbers. And that's why I wanted to use the complex numbers here, because if you're not working with the complex numbers, some polynomials don't factor completely, something like x squared plus 1. We know that the roots of this polynomial, so if you set this equal to 0, you get x squared is equal to -1, and so the roots are I and plus or minus I, and that's a problem, because if you're over the real numbers, you can't use those, you can't use I. So that's why we're working over the complex numbers. We want our polynomials to factor. And I wanted to put an nth degree polynomial that looked like this. P lambda is A0 plus A1 lambda, so on. Just repeating what I have up here. This thing is going to factor into n factors. So what I'm saying is P of lambda can be written this way, as lambda minus lambda 1 to the power m1, lambda minus lambda 2 to the m2, dot, 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 lambda minus lambda k to the mk, where m1 plus m2 plus mk is equal to n. So this is like saying x minus 7, x plus 2, x plus 9. This could be that squared, this could be cubed, this could be to the first power. So the thing is, we're factoring a polynomial, and because it is degree n, the factors here, if you sometimes you're going to have, you know, like x minus 2 squared or something, as long as these m's add up to n, it will be an nth degree polynomial factored. And these li's here, they're distinct. So they're distinct eigenvalues. Because if I had more than one of them, I would raise it to a higher power. Great. Now these numbers, m1, m2 to mk, they're actually called the algebraic multiplicity of this characteristic polynomial. So the values m1, m2 through mk, they are called the algebraic multiplicities of the eigenvalues. So let me tell you what I mean here. So let's say we have the polynomial lambda minus 5 squared lambda plus 3 to the 9th. And let's throw in a lambda minus 1. So if I ask you, what's the algebraic multiplicity of lambda equal to 5? So when lambda is 5, the algebraic multiplicity is equal to 2, because that is the power on this linear factor here. And then when lambda is equal to -3, so you see how we have these minus signs here? So this is going to be your eigenvalue. It has to have a minus. So this is the same thing as lambda minus a -3. So when lambda is equal to -3, that's going to be an eigenvalue. And the algebraic multiplicity is going to be 9. And when lambda is equal to 1, the algebraic multiplicity is equal to 1. Okay? So for each eigenvalue, there's an associated eigenspace, which is the set of vectors that go with that eigenvalue. So how do we find this eigenspace? So we had this matrix A minus lambda I, that when we multiplied it by x, we got 0. And we're trying to find all these values, these eigenvectors here, if we know a particular eigenvalue. So if this eigenvalue is 5, we want to find what vectors give us this a times x is equal to 5 times x. And that's actually the null space of this matrix. So the null space of A minus lambda I is the lambda eigenspace. If I put a lambda I here, it's the lambda I eigenspace. So that's important. Let's put that in a different color. It's red. And we also want to say something about the dimension. The dimension of this space is called the geometric multiplicity of the eigenvalue lambda I. So we have an algebraic multiplicity, which is the power of the linear factor lambda minus lambda I. So if it's like lambda minus lambda I squared, then the algebraic multiplicity is 2, and that we're getting that from the characteristic polynomial. And the geometric multiplicity of lambda I is the dimension of the eigenspace, the associated eigenspace, or the nullity of this matrix here. An interesting fact is that for each eigenvalue, lambda I, we have that 1 is less than or equal to the geometric multiplicity, and that's less than or equal to the algebraic multiplicity. So what are we saying? We're saying that the dimension of the eigenspace for some lambda I is always going to be less than or equal to the algebraic multiplicity. So that's the power on your linear factor. So if we had that the polynomial looked something like this, then the eigenspace that goes with lambda is equal to 3, the dimension of the eigenspace is going to be 1 or 2. If you have a power 1 here, then the dimension of the eigenspace has to be 1, because it's between 1 and here the algebraic multiplicity, which is also 1. So here you might have only one basis vector for the eigenspace, or you might have two. But for this particular eigenvector, you will have one basis vector for the eigenspace. And trying to think of what I'm not sure what I was writing here. I think that has to do with what I just said, so I'm going to erase that. Okay, so let's look at an example and put all of this together. I think that's the easiest way to understand it. So here I've given you a 3x3 matrix. I want to find all the eigenvalues, the associated eigenspaces, and the algebraic and geometric multiplicities of the eigenvalues. Okay? So what we're going to do, step 1, we're going to find A minus lambda times I. Okay? So we're taking 2, 1, 0. Maybe I should do this in a different color. Let's keep it in black so we can put our steps in blue. So 2, 1, 0, 0, 2, 0, 0, 0, 2. I want to subtract lambda times the identity. I'm going to write this in a lot of detail the first time we do it, and then in the future, less detail. So we want to use the 3x3 identity matrix, and I'm subtracting lambda times this identity matrix. And so I'm going to send in this lambda to everything. So this is lambda, lambda, lambda. And so what I'm going to get is 2 minus lambda, 1, 0, 0, 2 minus lambda, 0, 0, 0, 2 minus lambda. Okay? So that's our first step. The second step is to find the characteristic polynomial which is the determinant of this matrix. Alright, so we have this strange matrix and we want to take the determinant. Now remember, we have a long formula for the determinant. It says to go down a row or a column. You choose which one you want to go down. I'm going to go down a column that has 2, 0 entry, so let's do that. So the determinant of 2 minus lambda 1, 0, 0, 2 minus lambda 0, 0, 0, 2 minus lambda is 2 minus lambda times negative 1 to the 2. Then we cross this one out and this one out. And then we take the determinant of this matrix, which is 2 minus lambda squared minus 0. Okay? And then if you go down this column, you're going to get minus 0 plus 0. So if we simplify this, this is 2 minus lambda times 1 times 2 minus lambda squared, which is just 2 minus lambda cubed. So our characteristic polynomial is 2 minus lambda cubed. And from here, we can say that we have one eigenvalue, and that eigenvalue, if you want, you can write this in the form that sorry, I just wrote the same thing over. I'm factoring out a negative 1 from each one of these factors. So this is lambda minus 2 cubed. And so we set this polynomial, the characteristic polynomial, equal to 0. So if we set it equal to 0, and divide by this -1, we get lambda minus 2 cubed is 0. These are our eigenvalues, which is we just have one of them. And that is lambda is equal to 2. And from here we can go ahead and say what the algebraic multiplicity of lambda is. It is 3, because that's the power on this linear factor. And as a secret, we know that the eigenspace has dimension 1, 2, or 3. Okay, it's not really a secret. That's something we said, but just something to keep in mind. Okay, so we found our eigenvalues. We only have one. We found the algebraic multiplicity. So I think this was step 2. So now we're going to figure out the eigenspace. So this is the here we only have one eigenspace, so we need the 2 eigenspace. Okay, so to find the 2 eigenspace, we need to find the null space of A minus lambda I, which is now a 2. So how do we do that? Well, we need to plug in 2 times I and then subtract it from our matrix. Remember, A minus lambda I was equal to 2 minus lambda, 1, 0, 0, 2 minus lambda, 0, 0, 0, 2 minus lambda. So if we plug in 2 into each one of these, we get that we're looking for the null space of 0, 1, 0, 0, 0, 0, 0, 0, 0. Okay, how do we find the null space? Remember, we're looking for, let's call this matrix C. The null space of C is the set of all vectors x such that C times x is equal to 0. So we just need to make an augmented matrix. Let's put it here. 0, 1, 0, 0, 0, 0, 0, 0, 0 with a column of zeros. This is our x1, x2, x3. And we need to solve for this one here. We get that x2 is equal to 0, and x1 and x3 are free. So the null space of C is equal to all vectors R0, S, such that R and S are complex numbers. And we can find a basis for this null space. So the basis is going to be the span of these 2 vectors 1, 0, 0, 0, 0, 1. Since R and S are free variables. So as you can see, the null space has dimension 2. So the geometric multiplicity of the eigenvalue two is 2, which is less than the algebraic multiplicity, which we found to be 3. Okay, just as a fun extra step, because we found everything we needed, I want to actually see for myself that a linear combination of these vectors is indeed an eigenvector that's associated with the eigenvalue 2. So recall that our original matrix was 2, 1, 0, 0, 2, 0, 0, 0, 2. And let's choose some linear combination of these two vectors. I'm going to say the vector 5, 0, 4, which is 5 times this one and 4 times this one. Let's multiply this. We get 5 times 2, which is 10, plus 0 plus 0, then 0, 0, 0, 0, 0, 8. And you can see that this vector here is equal to 2 times 5, 0, 4. So it does, in fact, belong to this eigenspace, the span of these two vectors, and is associated to this eigenvalue.